So this is chapter 8, liquefaction of soil. And this is live recording during class soil dynamics BiT-CEng 7141. And content-wise, we'll see some liquefaction mechanisms and some case histories, types of liquefaction, ground failures, and with case histories, you will see the evaluation of liquefaction and the mitigation techniques. And finally, we'll see liquefaction modeling approaches, either using lab centrifuge tests and check table tests. We have seen these tests in chapter 5. They are the same tests which can use to simulate liquefaction for advanced research. And we can also simulate liquefaction in numerical modeling. Like Flax 3D has liquefaction modeling capability lately using the fin model and other constitutive models. PFC 3D, that's a discrete element method software. It can also simulate liquefaction. And there should be other softwares too. So liquefaction, the way it happens is, let's say you have a soil grain. Let's say you have saturated soil grain. You need water for liquefaction to happen. So normally, those grains are in contact. All these yellow arrows are there showing you contact. So there is some friction resistance. That's how the soil develops the shear strengths. But if you have some shaking, then these particles may settle down, especially in the case of loose sand. If it's clay material, you don't see that densification so quickly. But in that small duration of seismic event, you can have a quick densification of these particles. And when they try to densify, the water doesn't get enough time to go out through the pores. So what happens is you develop high pressure, high water pressure. If you have high water pressure within the pores, see what happened to some of those contacts. The soil particles, they are suspending, right? So some contacts are lost. See it, for example, around here, right here. This contact is lost. There was contact here, now we don't have it because the water has high pressure because the soil is compressing it, the soil above, and the particles are suspended. And if further increases therefore water pressure, then what happens is the water pressure can escape and cause a sand boil. And the whole thing acts like a semi-liquid. So in liquefied soil, you have less contacts, soil particles are suspended. And the whole thing acts like semi-liquid or liquid. That's just a phenomena, just in short. So this happened in the past. During the Gata earthquake, we have seen this example in at least in a couple of chapters. And liquefaction is common in loose sand and silt deposits. If it's like a gravelly soil, there is enough pore space for the water to escape. If it is a fine-grained soil like high plastic clay, then those high plastic clay, it doesn't compress so fast. So the water pressure doesn't develop so quickly. But there is a specific case for a loose sand and some silt deposits where it tries to densify so fast and the water doesn't have enough time to escape, so high water pressure develops. So for this loose sand, very loose soil has a high liquefaction susceptibility. If it is dense, it doesn't have that much liquefaction susceptibility. So here is a question. Why the denser soil is a less liquefaction susceptibility? Fakad. Why, if it is dense, why we have low susceptibility for liquefaction? That's what I'm saying in these arrows. The denser a soil is, or let's say this is a sand soil. The denser a soil is, the low liquefaction susceptibility. Why is that? It's already dense. It's already dense, so it doesn't really collapse to densify more. It's already in dense state. So even if you shake it, it's already dense, right? So it doesn't compress the soil further. If it is loose, as soon as you shake it, what happened? Phew, yeah, then it compresses the water. So that's why the looser the soil, the high susceptibility for liquefaction. That's what this table is showing you. Geological factors that influence the degree of liquefaction in saturated sand or silt include young alluvial deposits, which are typically porous or loose sands and silt, especially those river deposits as you see, because when the river flows, it brings sand and silt, and through time they accumulate, right? It's not dense. If you have sand and silt way down here, it gets compressed through time and it gets densified through time. But those river deposits, alluvial deposits, they call it. It's usually loose, something like this. This is Copper River, Alaska. It's a loose sand deposit. So this deposit through time, it can get even much larger. It can cover a large area. So if a seismic event happens, these areas, if there is saturated water, saturated soil, they are susceptible for liquefaction. It's already loose, then we're shaking, try to compress, try to densify, then liquefaction occurs. Ground shaking is usually amplified in soil deposits, causing more densification in saturated soil and bring more probability of liquefaction. From wave propagation, what we have studied, let's say you have this bedrock. The wave has less magnitude, right? As soon as it reaches to the loose soil, it amplifies a lot, right? That's what our impedance ratios tell us. If it is less than 1, you can see it, this area. Displacement amplitude gets much larger amplification. The soil is looser state and it gets shaken. Then this thing tries to densify. This is a loose deposit by the river. Then liquefaction can occur over there. You can see it also here. Hard igneous rock, when the wave passes, it's less magnitude, but the looser the material, the magnitude increases. Sedimentary rock, alluvial deposits, silt, and mud. So it gets much larger with the looser materials. Liquefaction mechanism in saturated loose sand and silt deposits. So if you have dry soil particles, assume these are soil particles. If you apply some time history, some seismic event, if there is no water, what happens? This thing densifies, it gets better, right? Gets better, gets denser. But there is at some point it may also softening can happen, cyclic softening. So if you shake it more, then you may exceed the shear capacity, you may lose it. But other than that, there is no water, it's not susceptible for liquefaction. But if you have water and apply seismic shaking, then you can, if it's especially loose deposit and try to densify, then that contacts get lost. If contact gets lost, your friction coefficient are getting loose. And you are also losing cohesion because there is no contact. So the general shear strength of soil decreases. When it is semi-liquid, we are losing soil shear strength. Now, grain-to-grain contact is partly controlled by packing, depending on how your soil particle packing is. If it is cubic packing, let's assume, just for understanding purpose, soil is much more complicated than this. We don't have irregular shapes like circles. But for understanding, let's see cubic packing. Each grain touches 6 other particles. You can consider the middle one. It's containing 6 other particles. Then let's see rhombohedron packing. Each grain touches 12 other grains. So here we are saying 4, but we are taking a section, right? Consider one in the front, one in the back. That's why it is 6. Here also same. Now, this, where do you have larger voids? Cubic packing or rhombohedron packing? The void space, it's larger in cubic packing, right? So which means this is loose state. It's not compact state. This is more compact. The void spaces are very little compared to cubic packing. So you can see larger shear strength. So the more contact we have, the more densities, we expect larger shear strength, right? So we have larger shear strengths here than here. There is a large void ratio here. Too many voids, very less voids here. Cubic packing, loosest possible packing. This is the loosest possible packing. You have large void space. If you have perfectly like this, only one particle touching other 6, then the porosity you can calculate from the geometry. About 47.6%. Porosity is volume of void by total volume. However, in the tightest packing, you have small void volumes or dense. Then N will be 28.95, very less porosity, because we have less void spaces now. Now imagine you have the loosest state, such as sand. Apply seismic motion, assume you have water in it. What happens? It tries to densify, right? When it densifies, what it is doing is compressing the water in between. If it is gravel material, if you have large enough voids, the water will have time to escape. But in this case, it's confining. So the high water pressure occurs. Shaking with loosest configuration with water result in tries to turn into a compacted state, but a high water pressure comes in between. Then rapid cycling shaking doesn't allow the sand to drain fast enough. So water carries the overburden and water pressure starts to increase. So this whole thing is trying to compact. Water pressure is developing. Grains adjust to tighter packing and you have your shaking. Then at some point, the water pressure increases. Water pressure go up and the overburden is also trying to come down. It's compressing even the water. We may have some good material at the top. During the seismic shaking, the soil tries to densify and the water is subject to the load of the overburden, which increases the pore water pressure further. Then grains can become suspended, right? We have seen that in the previous slide. When there is a high water pressure, now the grains lose contact. We know that water doesn't resist shear, right? So easily it's acting like a semi-liquid state, like a mud. Particles are floating because of the high pressure. Then at some point, the water pressure increases further, then it tries to find a way out, like a fountain, takes out the sand with it. And if there is some volume loss, what happens? There is a volume, there is a settlement. The whole ground can go down a little bit because the water is going out. There is volume reduction, so settlement occurs in the entirety. And it's so much complicated. This is like a level ground. We are not considering, structures like that. If you have a structure with shaking, you have lateral loads, differential settlement, overturning. Even in some cases, you have seen some vehicles being swallowed. The whole thing turning to, if you have a vehicle around here, it gets swallowed. That's what liquefaction does. So we call this sand, which comes out with the water, we call it sand boil. The sand is somehow boiling and coming out. It's actually taken out by the water, right? And there is a resulting settlement. Settlement can be irregular. You may not have uniform settlement depending on the ground. It can be a slopey or anything, but you will have some settlement. The original ground level hill is here, then the final is here. And you'll have your tighter packing now. But the damage is already done, right? That sand down here is now tighter packing, but it lost some water. It caused instability in the meantime. It was turning into the loosest combination. Particles were suspended. Once the water is out, once the ground is settling, now it looks compacted. That wasn't before. But in the meantime, the damage is already done. So that's just a model to describe liquefaction phenomena. But you can see this kind of sand boils in practice after earthquake. If the ground is loose deposit site, we don't expect this if the ground is a dense deposit or a high plastic clays, or it's like very gravelly soil. If it's gravelly soil, the water will have enough time to go from one place to the other, so it doesn't carry too much pressure to cause liquefaction. So these are some examples of sand boil surveyed in the field after earthquake. Alaska 2022, Boca del Tucayo, Venezuela 1989. So many places. So that's just the phenomena of liquefaction. Types of liquefaction, ground failures, and cases histories. There are two general types of liquefaction. Can be a flow liquefaction. This is like a flow liquefaction, like a flow pattern on the ground surface. If it is a slopey, the whole thing can go down. We call this flow liquefaction. Sudden and usually catastrophic soil deformation. Soil cannot stand under its own weight, such as slopes. It looks like a slope failure, but what happened is actually it liquefied and soil doesn't have any more resistance to carry the slope, so the entire thing collapses. So whatever you had here, you can look at it. Now it's down here. The entire mass is going down for slopes greater than 5 degrees. When it is a gentle slope, what happens is you can have liquefaction underneath, and the top part, before earthquake, this darker surface, you can see it broken apart after earthquake. Soil liquefies and moves in lurches, like a ratcheting effect. Cyclic mobility this is what we call cyclic mobility. It's very gentle slope, something less than 3 degrees. So it doesn't collapse like the high degree slopes, but the ground breaks apart and you can see it, because it's moving up and down. If it's flatter, even sometimes can move up and down, things breaking apart. Or if there is a gentle slope like this, you can see it's breaking apart and moving like this. And it causes the ground oscillations. So liquefaction alters ground motion. Now here is one observation. High frequency motion filtered out. It tends to amplify low frequency, high period ground motion. So what happens is, let's say you have a ground, right? And let's say this is bedrock. So some seismic wave, let's say shear wave, is propagating through. And we know the recording here. Let's say this is a bedrock. And at some point, somewhere in between, there is a liquefiable layer. This liquefies. This didn't liquefy, this didn't liquefy. This is just for example. Then what happens is the wave is trying to propagate, right? But in the meantime, let's say the wave is propagating properly up to certain state. Let's say it depends on the state. In this case, it looks like it liquefied pretty much right away. Then you see it, some kind of wave propagation. Then all of a sudden you see it, high frequencies filtered out. Only we see peak. Just by looking at the ground motion, you can say if liquefaction occurred. What happened to this high frequency motion? Because this thing is turning into liquid, it's not passing anymore, or semi-liquid. If it was one solid, same similar material throughout without liquefaction, you would probably see just some amplification on all high frequencies up to the top. But somehow, through the depths, the high frequencies are lost, and the low frequencies are only observed. This is because that liquefied layer, it's filtering out the high frequencies. It's passing only the low frequency wave because it's turning almost like a liquid, right? As if it's purely liquid, what happens? Even a shear wave doesn't propagate through it. You may not even see this at all. You'll just see something flat. But it's not purely liquid, it's semi-liquid. So it's filtering out, it's getting too soft. So only the low frequencies are passing. So it can modify the seismic motion. It has advantage and disadvantage. The advantage is what? The advantage is all those high frequencies are getting filtered out, so little damage at the top surface. But the disadvantage is this happened because of liquefaction, so nothing may survive at the top because the ground is very unstable. Is that clear? General ground failure resulting from soil liquefaction. We can see sand boils, sand coming out of the ground. We can see lateral spreads, which is especially in sloping ground, the whole ground is laterally moving. Loss of bearing capacity, because we are losing contactors. Ground settlement, the water is coming out. Flow failures of slopes, the whole slope can collapse. A ground oscillation, like lurching. Lift up of buried structures, tanks and manholes, we'll see this. Lateral spreading is if you have a gentle slope, the ground is breaking apart and moving somehow. These are practical examples of lateral spreading. It looks cracking happening everywhere, but it's basically the soil underneath is liquefied, and this is like a lateral spreading occurring. This is lateral spread at Dharmora, Puji, I think this is India, 2001. The damaged sewerage structures or buried structures. It's very interesting phenomena for buried structures. Those sewer pipes or even like tunnels like that. Tunnels may be deeper, but if there is a shallow depth and if liquefaction occurs, what happens is because of when liquefaction happens, what happens? This is high pressure, high water pressure underneath, right? So it lifts up the tank. The water tries to go up, but there is a solid concrete, so it pushes it up. And what happens is it breaks the pipes, concrete pipes nearby. And you'll see this buried structure coming out to the ground surface. This is a good example. This was underneath, now it moves a little bit up. Manholes, they are usually built flat, right? We don't build manholes like this with height. But when liquefaction occurs, they are coming out. You can see another one right here. In the middle of the road, you have a manhole coming out because of liquefaction. Lifted up manholes. This is Tokachi Oki earthquake 2003, I believe, probably in Japan. Lifted up manhole and gushed soil during liquefaction. The damage of embankment structures. You may have a slope even with a retaining structure. You may design it very good. But if this soil liquefies, then the entire thing is moving. The entire embankment is failing. And lateral spreading, this is moving this way and this is moving this way, so this thing is going down. Big settlement. That's what happened, this embankment, I think. You have this section for the embankment, then soil underneath liquefied, this is moving other side, this thing is going down and cracking. Or Lower San Fernando Dam 1971. See what happened right here. This is the dam section. This thing is like a going down and laterally spreading. Upstream slope failure. Failure of retaining wall, Kobe 1995. This is a retaining wall with a slope, but the soil underneath is liquefied. So the entire thing is just messed up. Building tilting and overturning during liquefaction caused by the 1964 Niigata, Japan earthquake. We have seen this picture in the introduction and other chapters. Cars being swallowed by the sand boils and pile foundation getting severely loaded, breaking, buildings tilting and falling. Earthquake of July 29, 1967, Caracas, Venezuela. So the entire building is tilting, going down because it's sitting on a liquefied soil during the earthquake. This is unusable after this. Lateral spreading damage on gentle slope. Nisqually earthquake 2001, Washington. This is in US. So this is the entire road laterally spreading because the ground underneath is liquefied. 1995, magnitude 6.9 Kobe earthquake. I don't know, but maybe this is lateral spreading the cracks. You can see the size of the crack compared to a human being height. Pretty large crack. And this is happening, imagine, they're very close to a bridge, right? This is a bridge. 1965, magnitude 6.5, Seattle Tacoma earthquake. This is in US. Slope failure. Looks like this is near to a river, but the slope is failing. This is a road. Kobe earthquake, 1995. See, this is lateral spread cracking. If the ground moving sideways, what happened to these piers? Moving away from each other. And the deck is falling. Displaced quay walls, Kobe 1995. This is like a porting. See here what happens. So those are some case histories already surveyed and recorded, documented from several earthquakes worldwide. Unfortunately, no example in Ethiopia. That's good, right? We don't want earthquake. And no major earthquake expected in Africa because what's the reason? All the major earthquakes are in the Ring of Fire area, the Japan, the US, West Coast, or the Middle East, Himalayan mountain, and no major in Africa. Ellen, what's the reason? What's that? Yeah, the tectonic plates, we have mostly diverging plates. Diverging plates, they cause minor earthquakes, so no major earthquake is expected in the African continent. Section 8.2, liquefaction evaluation. It's well known that poorly graded cohesionless soil sand, loose sand to silt can liquefy. Most of the loose sand and some silt can liquefy. And researchers also argue that low plastic fine soils, even some clays with low plasticity, clay and silt, can liquefy too. Idris and Blanca, these are very famous guys. They did a lot of research on liquefaction, developed procedures for design. They are in US. So Idris and Blanca in 2006, Bray and Sanko in 2006, they developed this chart. So even fine-grained soils with plastic index of within this range, less than 12, can show some liquefaction. It may not be as bad as loose sand, but they can cause some kind of liquefaction. So Plastic index less than 12 we call it susceptible for liquefaction based on this study. So don't expect it to be only loose sand. Some silt and clay with low plastic index can also liquefy. But if plastic index is greater than 12, 20, cyclic softening, no liquefaction. It gets soft, but it doesn't liquefy. Beyond 20, we don't expect much in terms of liquefaction. This is just a definition of those soils, ML, CL, the silts and clays from the previous chart. You can go through it. Initial liquefaction occurs when pore water pressure equals the effective confining stress. Now let's go a little deeper into evaluation of liquefaction. There are equations that you can use to show if liquefaction is going to occur or not. It's not only having a loose sand. For liquefaction to occur, what should happen? The water pressure that's developing, it should be exceeding the effective stress at that depth, right? If it exceeds, then it's sand boil is occurring. The water is coming out, right? That should happen. So it's saying initial liquefaction occurs when pore water pressure, the one increasing due to the seismic event, equals the effective confining stress. If there is some effective confining stress, if the excess pore water pressure increasing, and it's equal to the effective stress, now we are reaching a point of like zero effective stress at that depth. Further increase, the whole thing liquefies. So this is pore water pressure ratio, which means excess pore water by the effective stress at that depth. You don't see it greater than 1 because as soon as it reaches the effective stress, it liquefies. So this can happen, let's say you have a times 3 motion here. This liquefaction can happen, let's say in the first 5 seconds. Pore water pressure was increasing. Then when it reaches 1 or around 1, then it liquefies. This is what shows you liquefaction. The ratio of the pore water pressure by effective stress. Then in this area, it's liquefied state. After around 35 seconds during the earthquake, you see it going down. This is mainly because the earthquake shaking also decreasing. So the main energy of shaking is in this area. Or at this time, probably the water escaped and the soil is getting denser. So it's trying to gain its effective stress. So this chart is very well known to predict liquefaction. And those tests, check table tests, a centrifuge test, those are producing a result like this. You have seen that check table test where a lot of instrumentation is in it at every depth, pressure sensors and things like that. That's what they're producing. Finally, you can plot it a result like this. You know exactly at every depth when the water pressure increase, and you know what time the effective stress is equal to the pore water pressure. So as soon as the pore water pressure increase and equal to effective, then it's liquefying. So if you see a chart like this, time versus pore water pressure ratio, and then reaching around 1, then that's liquefaction. When you model also in softwares like FLAC using fin model, this is the output you get at every depth. This is for a specific depth. We are comparing pore water pressure increase versus the effective stress at that point. Effective stress is constant, but the pore water pressure is increasing. At some point, it's equal and exceed, and the whole thing liquefies at that depth. Sample excess pore water pressure plot for liquefaction. Lab, shake, table, or centrifuge, or numerical simulation. Liquefaction develops at different times along depths of soil depending on stress state. So there is a certain depth that liquefaction occurs. It doesn't happen at the same time in all depths. It depends on the state of stress. For the top of the model, when we say model, we mean layers. Let's say this is bedrock and you have a loose sand deposit. Let's say we are monitoring this pore water pressure plot as 3 depths, 1, 2, 3. So let's say this 1, 2, 3 at the center of these layers. Top of the model, it may reach quickly. Middle of the model, it may take some time because effective stress is higher. So the water pressure also takes some time. Bottom of the model, it may take some time. So this one happened around 2 seconds. This one happened around 7 seconds. This one happened around 20 seconds. If we don't have enough shaking, this is dynamic time history of shaking. If the earthquake is for 15 seconds, we may not even see liquefaction in the third layer. So the state of liquefaction depends the initial stress state. And usually observation is that it occurs at some depths below certain level, below 2 meters or something like that. That's the critical depth where it reaches quickly and liquefaction starts. But by putting those monitoring transducers, pressure meters, you can really calculate in the lab test. Either lab or softwares like Flag also can give you. Do a dynamic analysis and just soil only. Then it tells you when liquefaction is occurring. The potential for liquefaction, factor of safety, can be expressed in terms of capacity and demand. The beauty is researchers in the past, Boulanger et al., they developed a way to evaluate for liquefaction. You can go to a site, do some measurement, or do some kind of software analysis, and you can find factor of safety against liquefaction. You can, do a general judgment. If you see loose sand, you may say, oh, this can liquefy. But by doing some experiment testing, you can also get a factor of safety, pretty close, a factor of safety, pretty in good estimation. Factor of safety against liquefaction, it's clear. The capacity or the resistance of a soil by the demand give you the factor of safety. Demand is what? That's the seismic motion or the stress caused by the seismic motion. Capacity is the soil shear strength capacity right before liquefaction occurs. So it means resistance by loading. The limiting value by the cyclic loading. Factor of safety against liquefaction, so it's pretty much the same equation, just more clarification. If we normalize the cyclic shear stress by the effective vertical stress, then we get the limiting stress or the capacity of the soil normalized by the effective stress at any depth. We call this CRR, cyclic resistance ratio, because this is a resistance. This is a soil capacity, cyclic resistance ratio. And this is cyclic stress ratio. The seismic demand divided by the effective stress at that depth. It's a stress. It's caused by the seismic. This is by the earthquake. This is the capacity of the soil. So we are going to evaluate if a soil liquefies or not. CSR, cyclic stress ratio, this is a seismic demand. CSR can be obtained either from site response analysis or from simplified methods. Site response analysis, we're going to cover it in detail in chapter 9, next chapter. But to simply explain it, if you do analysis like a site response with software, programs like Shake, they model the soil and apply time history motion and understand the behavior of the soil. You can find the stresses at any depth during a seismic event. So model the soil in Shake and apply input motion. You have different layers of soil. And what Shake can give you is it can give you the seismic stresses or the demands at any point. The shear stress is caused by seismic. So you can find it from the software, which means, in software, it means first you have to do your geophysical testing, lab testing, get the soil dynamic properties. And one input for shake is what? The strain compatible properties of soil. Remember those degradation curves, Gigi-max curve and damping curve? They are direct input for site response analysis in shake. That's how you represent the soil. They can be obtained from the lab or from field tests like geophysical testing, but they will be input for site response analysis. So you do a site response analysis, and that input you put here is expected earthquake for the site. Once you apply it, now you can get what actual shear stresses the seismic is causing at any depth. So that's your demand. That's the CSR, cyclic stress ratio. And the stresses we get here, we'll divide it to normalize it. We divide it the effective stress at that depth. I think Sheikh automatically give you the CSR. Or there are simplified methods also. So we will see the concept of site response analysis in chapter 9. Tomorrow we'll see it. So you'll understand better over there how Sheikh works, what's the principle behind. So this is like analyzing the soil alone. If we are adding some building on it, some structure, now this is going to be SSI. Soil, structure, interaction. Normally, we do first the soil part without the structure. That's what we call site response or ground response analysis. If we are modeling also the structure, that's when we call it soil structure interaction. In some cases, research cases, you may even model the water inside the soil. Now you're modeling liquefaction. If you are using saturated soil, you're modeling. Imagine you have, let's say, loose sand, times 3 analysis, structure. So you're modeling actually a realistic case, like a liquefaction case. But for now, let's focus. Assume no structure here. It's a ground only. We are doing ground response analysis. To get the seismic stress at any depth, we divide it by the effective stress there, and we call it CSR, cyclic stress ratio. Our researchers, so Sheikh program ground response analysis. We'll see it in chapter 9 in detail. Or there are other techniques. I mean, this is so much sophisticated. That's how it's done these days, using softwares like Sheikh or SASI, or even FLAG can do it. In FLAG, usually I think they have both options, but strain compatible properties and also cognitive models, real dynamic analysis, but it's so much time taking. So the best way for ground response analysis in Sheikh is using strain compatible properties or degradation properties. It's so quicker. The other option is to use simplified method. In simplified method, let me see if there is anything I'm missing. This is still the Sheikh approach. So once you do the Sheikh approach, let's say you apply time history, get at any depth, you get the CSR, and you divide it by the effective stress. So in the entire depth, by monitoring points at different depths, you can plot the curve actually. You'll find the CSR chart. This is coming from softwares. In CSR, because the motion is so high frequency in some cases with peaks, usually the recommended values to consider 65% of the max stress. If this is the max stress, we usually consider 65% at all depths. Now, do this. This is a shear stress we are recording. If you are doing a time history analysis in Sheikh, this is a shear stress you get at any depth. This is just one example. It's maybe at this depth. Use 65% that max value. Now monitor the values at several depths and connect the lines. Finally, this is what you get. So this is a CSR with depths from softwares. Or the other approach, which used to be done in the past, even now it's very popular. I used this method to estimate, both ways, the simplified method and the shake approach. The simplified method, this is older, before even the shake was born, I believe. This is 97 one. Shake was developed in the 1990s. Seed and Idris, 97 yuan, assumed a rigid column of soil. This is the ground. They assumed a rigid column of soil and used the maximum acceleration at peak ground acceleration to determine the maximum stress at any depth. This is the ground, right? And during the earthquake, this thing is moving with the ground. The ground is, what did we say in ground response spectrum analysis? It's so rigid, right? So they are using the PGA. It's like the zero period acceleration. So that's okay to use. Remember, for slope stability, we said we can go up to PGA or some 80%, 20%, or 50% reduction. But this is on the ground, so this is assumed to rigidly move, and they are using PGA. It's okay. Assuming the soil column to behave as a rigid body, the maximum shear stress at a depth h due to a maximum ground surface acceleration, Amax, can be given by, this Amax is from the time history. If you have a time history, that Amax is the peak value, or that peak value corresponds to the PGA, zero period acceleration. So they modeled this, just they assumed some soil column, they assumed it rigid, they assumed Amax to be constant throughout up to a certain depth. And the max shear stress at this base from the soil weight, they assumed to be, they got effective stress, Amax by G. It's simple math. The uniform cyclic shear stress with a reduction factor already to account for soil flexibility. Now, initially they assumed this to be rigid, right? But rigid assumption is a little bit tough. Soil can be a little bit flexible, right? We cannot consider a rock and soil to be equally rigid. So for soil flexibility, they introduce some other factor, RD. And they further reduce that cyclic shear stress by RD. The CSR then is given by, this is the cyclic stress caused by the seismic. Then if we normalize it by the effective stress, it's going to be CSR, cyclic stress ratio. Just so that you can do this manually. If you can do this soil column for different depths, you can develop it by hand. So that's how they developed it in 971. This is too old. Nowadays, we're lucky we have the Shake softwares. We can model it and automatically give us more realistic value. But this is, usually when they come up with analytical solution like this, it tends to be a little bit conservative. It's simpler to do it by hand in Excel or MathCAD, but at the same time, it's conservative, a little bit uneconomical. That RD, shear stress reduction factor, they provided this table with depths. At different depths, flexibility of soil changes. So the RD value changes. And there is average value or range for different soil profiles, depending on the soil type. Usually it's the recommended value to use the mid value, the mid range. So depending on where you are, at 20 feet depths, at 60 feet depths, at 90 feet depths, you can use average value for RD in the previous equation here. So that was the cyclic stress. That was the demand part. Now we're coming to the CRR, the resistance part. The cyclic stress part, that's what you get from the seismic. The force caused in the soil by the seismic. But the soil has its own capacity. The soil has its own capacity. So the capacity of the soil is where we get CRR, cyclic resistance ratio, soil resistance or soil capacity. So from lab tests, they developed also the capacity of the soil, the CRR. from previous case histories, field tests, and lab tests, Seed et al. In 1975 developed simplified relation for CRR for earthquake magnitude of 7.5. He developed this chart. For example, if you have any blow counters like SCPT test, if you get it, you can pretty much get the CRR. This is, even if it says CSR, it's basically the capacity of the soil at the limiting case, which is CRR. So even if you see CSR here, it's CRR, or they call it sometimes CSRL. So CRR for clean sand with no fineness. He developed this average value. From field tests, he estimated a lot of data. He came up to say this. For what magnitude of earthquake? 7.5. What happened? But earthquake doesn't happen 7.5 all the time. So he introduced some correction factors for other magnitudes. For 5.25 magnitude earthquake, is a correction factor is 1.5. Magnitude M, CSR, that magnitude divided by the 7.5. For 7.5 earthquake, it's 1. That's where this chart is. But for others, there are correction factors. And he also introduced, Seed et al. In 1975, he introduced with sand with some fineness. 5% fineness, less than 5%, 15%, 35%. So he provided this chart for the capacity of the soil, for the CRR part. And same correction factors. So now, factor of safety, simplified method. So general equation is the final equation for liquefaction factor of safety using the simplified method is the CRR for that magnitude of earthquake by the CSR, which is the demand part, seismic stress part, and the top one is the soil capacity, resistance. So it's the CRR, MSF is earthquake magnitude magnification factor, and K is overburden correction factor, and K alpha is initial shear stress correction factor. And CSR is the same equation that we have seen, 65% reduction from the peak. They use the max PGA, the max acceleration, normalized with the effective stress, and RD is a reduction factor for soil flexibility. And this is what it looks like. In general, if you find that CRR at different depths using these charts, this is what you get. This one, we already got it, right? Using like something like shake, the CSR, we get it. The CRR part, the soil capacity part, normally it's something like this. But factor of safety, how we define it? It's CRR by CSR. Cyclic resistance ratio by cyclic stress ratio, or capacity versus demand. Now see this chart. This is a pretty common chart. If the capacity of the soil larger, do we expect liquefaction? This factor of safety, if it's more than 1, do we expect liquefaction? No, the soil is stronger than the stresses caused by seismic, so we don't expect liquefaction, right? So for liquefaction to occur, this ratio, the factor of safety should be less than 1. So you don't want this factor of safety to be less than 1. If it's less than 1 means seismic is causing larger stress, shear stress in the soil than the capacity of the soil, and liquefaction can occur. Which means seismic is tricky. What it does is it applies stress, it increases water pressure due to densification. Soil particles get suspended, they lose shear stress, so it reduces the shear capacity of the soil. So see this chart. At some depths, the resistance of the soil is less than the stress caused by seismic. See this region. This is larger, right? The shear stress by seismic is larger than the shear stress, the shear capacity of the soil. So in this area, what do we expect? Liquefaction. So this is we're getting into the evaluation. If we compute the CSR throughout the depths of your soil layers, and if you compute CRR through the depths of your soil, and compare the two, if there is overlap, then we are in trouble. Overlap means factor of safety is getting less than 1. This is the concept behind how to estimate if subsoil liquefies or not. What time is it? Should we go further a little bit or you tired? Finish? Okay. Let's go a little. Let's see this example and see a little bit and we'll see it. So this is an example on liquefaction evaluation from Kramer book, reference 1, example 9.4. This is 1964 Niigata earthquake magnitude of 7.5. We have seen liquefaction from this earthquake in so many pictures, case histories I showed you before. This is the same earthquake. But researchers didn't investigate the site before the earthquake because in those days, we didn't know what liquefaction is. But once it happened, when we see buildings collapse, tilt, vehicles getting absorbed in the soil, then we realize something else is happening. Then people start evaluating. So let's see the situation. So normal ground at that point is up to 1.5. Below 1.5 depth, there is groundwater. And blow count in those sites, corrected blow count for SPT test, it's this much versus depth. So a site in Japan underlain by clean, potentially liquefiable sand was described in example 6.6. So I brought it. This is example 6.6. It's in the previous chapter. We are in chapter 9 now. But I brought those, what was done there. They did a soil investigation, come up with a blow count, where the water table is. So we have it here. SPT tests were performed at the site using standard Japanese SPT technique, the process by which the measured SPT resistance are corrected to obtain N160 blow counts. This values was described in example 6.6. So this is what's described there. Using the information available, determine the extent to which liquefaction would have been expected in the 1964 Niigata earthquake if the peak horizontal acceleration at the ground surface is 0.16 g. We know the peak ground acceleration. There were recording stations, so we know how much it is. And we know the soil stratification, at least the blow counts. We have some softer layers, you see 9.3, 15.2 blow count. So this is, the lower the blow count, the softer the soil is, the looser it is. So we have some soft pockets, soft layers. See this. This 28.1, 22, they are good. But so many soft layers in between. And it's a saturated layer. So let's see one specific layer for liquefaction evaluation. Our goal is to find the factor of safety for liquefaction and see if it is less than 1 or greater than 1. So this example specifically focuses on at a depth of 6.2, just to show you an example. For other depths, you can repeat the same thing. You can put it, set it up in Excel or MathCarry and compute all these numbers. So at a depth of 6.2, total stress at depth of 6.2 meter, column 2, this is a total stress column. You can find that and get 128.1 kilopascal. And you need to include water also. Its water is at 1.5 meters, so it's a saturated area. So anything below here, it's saturated. From figure 9.25, the stress reduction factor is 0.96 for these steps. The cyclist ratio CSR is, let's see, 9.25 depths of 6.2. This one, 9.25 depths of 6.2 around here. So RD, that's how you estimate it. Pretty 0.9 something. .96 is RD. Then the cyclic stress ratio is, we take 65% peak ground acceleration, total stress, RD, you get 12.8 kilopascal. So cyclic is 12.8. This is this column. So RD is also this. We already got 0.96. So it's giving you this line, this calculation. Using figure 9.3 clean sand, fineness less than 5%, the CRR cyclist ratio limiting for 11.7 corrected SCPT block count, 9.3, 11.7. For clean sand, SCPT corrected is around here, 11, so you get the corresponding value, little above 0.1. 0.13. The limiting shear stress, we multiply it by the effective stress, then we get 10.7. Where are we? We are right here, effective stress. Now, the factor of safety is the CRR by the demand. CRR is a limiting condition right before liquefaction offer, that's the soil capacity. And the demand, the seismic part is this. So we get a factor of safety of 0.84, this value. Is it going to liquefy or not? Yep, it's going to liquefy, at least based on this analytical approach. Anything less than 1 liquefies. So we do this. I mean, it's not easy, it would be tedious to do it by hand, but you can implement these equations in Excel or MathCAD and get all this and get the factor of safety. Your factor of safety is 0.72, 0.35, in some cases more than 1, 1.66 doesn't liquefy, but see this soft layer also, 0.29, 0.43, 0.35. So in my experience is, if you see corrected block counts less than around 12, less than 10, expect liquefaction if it's a saturated area. But it depends on the depths also, because effective stress matters. The initial stress condition matters. So if you plot that factor of safety, this is what you get. Or due to earthquake, you have this CSR and you have this CRR. So if you see factor of safety plot, you see in some depths, it's more than 1. So this is the areas which liquefies. So we realized this is done after the earthquake. After researchers came up with the realization of liquefaction, and they came up with techniques, analytical approach, and they evaluated. When they evaluated, they get a reasonable value. The soil actually liquefies. Before the earthquake, they didn't know this. Before 1964, they didn't know this. If there was this understanding, they would have done something. At least they will evacuate equipment, people from the buildings, things like that. But they didn't know. This is in the old days. So we learn from history. So even, a simple hand calculation with a field data, you can, get a good reasonable value if the soil liquefies or not. Nowadays, there are softwares to help us. As far as you have a good data, good input from lab tests or field tests, you can come up with, much better results. So you can estimate liquefaction like this. So liquefaction evaluation is a pretty common task now for civil engineers, geotechnical engineers, especially in high seismic areas. I have done a lot of this by Excel and math card like this, the way exactly I'm showing you. Once we get the field data, we just implement this equation and evaluate for liquefaction to see if liquefaction occurs. Or in some cases, we use the softwares to show us if liquefaction occurs. So this is common to do in US, in Japan, Asia, Middle East, Northern India, depending on if you have, those kind of deposit. You may not find it in Ethiopia, but that's how it's done. That's a geotechnical engineer. If you know there is liquefaction, then you'll do something about it. Your recommendations, what to build, or mitigating the soil not to liquefy, things like that. That's where we come to liquefaction mitigation. So if you know the soil, some layers liquefy, then we have to do something, or we should abandon the site. Selection of method for liquefaction mitigation, site improvement, depends on many factors. Location, area, depth, volume of soil type, properties, site condition, anticipated earthquake loading. For example, in Ethiopia, anticipated earthquake is insignificant. So even if you have a loose sand, you don't care much, right? Because the magnitude of the earthquake to cause liquefaction is not there. A structure type and condition, economic and social effects of structure, availability of necessary materials, availability of equipment and skills. There are so many factors to come into your decision, how to mitigate it. If it is so uneconomical, you may even abandon the site. Common liquefaction mitigation techniques include dewatering, removing the water. If you are able to remove the water from the loose soil, the loose sand, then if there is no water, there is no liquefaction, right? So locally, people remove the water, especially for existing critical structures. You can, arrange a pump and do some well around it and take out the water constantly. Stone columns. Remove liquefiable soil layer if possible, if this is before construction. Or compaction for loose soil. Before the construction, you can also compact that layer. So avoid the looseness from the get-go. Consider liquefaction resistant structures, like deep foundations, or a wider mat foundation. Avoid something like isolated foundation. Or in the worst case, you can even avoid the site, if costly to mitigate. Dewatering works by lowering water table below liquefiable soil. If you have critical infrastructure around here, and if there is liquefiable layer around here, then take the water out. At least you are lowering the water table and you are reducing the possibility of liquefaction occurring. There will be some cost in dewatering, but maybe better. So there should be some economical analysis. Or introduce stone columns. Stone column is where you don't have a borehole and replace the existing soil with some gravel soils. So what happens is the nearby water comes to the stone water and you can remove it. It's because seepage flow occurs. Or even if you don't take it out during the shaking, what happens is, because this is a stone column, the water have enough voids to go out, to flow freely. So introduce stone columns. Remove liquefiable layer. In normal construction, what do? You remove the soft deposit at the top, right? The peat and things like that. Same way, if there is a liquefiable layer in shallow depths, if it makes sense economically, then remove this entire thing and do your construction at this level. Compaction for loose soil or compact the soil. Densification of soil. Various methods of compaction. Roller compaction you can use, dynamic compaction, vibro compaction, compaction grouting, compaction pile driving. You compact the soil and make it dense at the beginning of the construction. Dynamic compaction. That's when you drop heavy weight and try to compact the soil. Vibro compaction. That's when you introduce a vibrator and compact the soil and replace it with some granular soil, refilling material. Compaction grouting, or you can introduce just some grouting to the soil. So you really change the behavior of the soil. Introduce grouting at many places. Compaction by pile driving. Remember that pile we saw a picture before? It's somehow we drive the pile. Well, this is a bad picture. And we compact the soil at the same time when we drive the soil. The pile, I'm sorry. 5 is, that is a site mitigation. That's how you prepare the site. You can compact it, remove it, dewater it, whatever you do. And at the same time, you can also do liquefaction resistant structures. If there is a bedrock nearby, then do a pile cap and socket those piles, tip points to the bedrock. Or introduce a shallow foundation, which is like a mat foundation. Covers a wider area, so the possibility of being inclination or being swallowed is little. Isolated foundation is probably the worst one when it comes to liquefaction. Isolated footing. A structure that possesses ductility, has ability to accommodate large deformation, adjustable support for correction of differential settlement, and having foundation design that can span soft spots. It's like a mat foundation, which can decrease the amount of damage a structure may suffer due to liquefaction. To achieve these features in a building, following aspect needs to be considered: shallow foundation aspect, deep foundation aspect. In shallow foundation aspect, if you have a liquefiable local zone, if the bigger area, this may not work. But if there are few spots, then even if this liquefies, your mat foundation can bridge to a good non-liquefiable material. This can survive, this can work. Strong mat foundation, even if some spots liquefy, it doesn't matter. But if you have so much to liquefy, still it's better than isolated footing, but there is a potential for tilting. Deep foundation aspect, we discussed this previously. You can socket the piles to the bedrock. Let's say this is a liquefiable layer, but you need to design the piles for the lateral loads. There is a huge lateral load from kinematic impact. Those Japanese techniques we discussed, apply the lateral loads on the piles in the non-liquefiable layer, and the liquefier layer at least 30% of the lateral load, soil pressure on the piles. So design those and allow some flexibility. Don't make it rigid. Usually we don't design this pile cap connection for moments. It's like only pin supporters. So there is some flexibility to move around. Or best thing is like a batter pile you can use, diagonal piles, so they take out the lateral loads. Like offshore structures against hydraulic tides and things like that. We have only 10 slides, we can finish it. Or are you guys tired? Okay. Section 8.4, modeling approaches for liquefaction. We have seen it like, we can call it a pseudo-static approach using the constant acceleration. You can do it by hand, right? Calculating the factor of safety. Or for research purpose, I showed you this video last time in Penn State. They are monitoring liquefaction for advanced studies. They model it, they put instrumentation at several depths, and they find output like this. This is for different layers from the instrumentation. So you can do a shake table test or centrifuge test to find the behavior of soil at several depths. So you can see this plot, liquefaction ratio, or this is called also pore water pressure ratio, the excess pore water pressure divided by the effective stress. When it reaches close to 1, then you see it getting horizontal in maintenance liquefaction. These are different depths. Or not only lab tests, but nowadays there is numerical modeling of liquefaction. Flax 3D using fin model, it can simulate liquefaction. There are softwares doing that nowadays. Flax 3D, new 3D liquefaction quantitative model, that's the fin model. US Minneapolis, Itasca. We're done. So main reference for this chapter, reference 1, S.L. Kramer, chapter 9, and reference to Braja Midas book, chapter 10, and so much from online. I wish I could list all, but those pictures, those case studies you saw, they are from available resources from Google online. They help us to learn a lot. In my time when I studied this course, I was not fortunate enough to see those pictures. But you guys are lucky, you can see it really and visualize it. So there is a lot of pictures from online resources. In some of them I mentioned where they came from, because we have to always credit to those people who documented it and make it available for free. In some cases I didn't. So homework problem, reading assignment section 9.4 and 9.5 of reference 1. That's a reading assignment. Just scan through it. I don't expect you to submit anything, or I don't expect anything out of it for a test, usually for just your own understanding.